Welcome to the Robotics Brief. I'm Alex.
And I'm Sam. Good to be here.
So this week, I've been struck by how much of the cutting-edge research we're seeing isn't about building new robots or even entirely new algorithms anymore. It's about optimizing what we already have and doing it with ever more subtle, indirect methods. We're getting really good at making the machines we've already designed or the models we've already trained work better or predict more accurately or simply understand us more deeply.
Yeah, it almost feels like the foundational breakthroughs are slowing, and now we're just in the make it actually work in the wild phase, or even more niche, the make it optimize itself even better phase. It's a lot of meta-level improvement, which frankly makes me a little skeptical about how much of this is truly advancing capability versus just improving efficiency.
That's a fair challenge, but consider something like MidTool, which we'll get into, or even the AI for AI bench paper. These aren't just efficiency plays. They're about architecting the learning process itself to be smarter, to bootstrap itself to higher performance thresholds. It's a different kind of innovation.
Okay, but is it architecting a smarter learning process or just finding a new way to shovel more data into the pipeline at a specific moment? Because those aren't the same, and one sounds a lot more impressive than the other.
And that's exactly what makes it interesting, Sam. Let's dig into that first one, AI for AI bench. This paper tackles the holy grail of recursive self-improvement, the idea that an AI could design better AI training algorithms for itself.
Right, the superintelligence pathway. Everyone's talking about how AGI could just self-improve its way to omniscience in an afternoon. But this paper isn't building that, is it? It's a benchmark.
Exactly. It's a benchmark specifically designed to isolate that particular ability. Can an AI actually design or improve the underlying training algorithm? Because most existing benchmarks for AI agent improvement are won by better data collection or hyperparameter tuning, not by fundamentally rewriting how the learning happens. That's a huge distinction.
Yeah, and that's the part that gets me. If you want an AI to improve itself, it needs to be able to change its own brain architecture, its own learning rules, not just find a slightly better learning rate. So what does this benchmark actually do? How does it measure that?
It focuses on something called the compute capability exchange rate. Essentially, can an AI propose an improved objective function or an update rule for its own training process? And does that new rule lead to more capability for the same amount of computational effort? It's trying to separate that algorithmic insight from brute force data or hyperparameter optimization, which honestly is a subtle but crucial difference for the whole RSI discussion.
I appreciate the goal, Alex. I really do. But it feels like we're still talking about improving the compute capability exchange rate, rather than designing entirely new paradigms of learning. It's like, can you make this car go faster with the same fuel? Not, can you invent a flying car? It's still within the same conceptual framework.
Well, even small improvements to that exchange rate applied recursively could compound dramatically. Imagine a 1% improvement in learning efficiency that applies to the next iteration of the AI, and then that improved AI finds another 1% improvement. That's how exponential growth happens. It's not about inventing a completely new car. It's about making the engine radically more efficient, which then allows you to do things you couldn't before. It's less about the novelty of the invention and more about the multiplier effect.
That's the theory, anyway. I'm just not sure the benchmarks fully capture that kind of breakthrough yet. I mean, they're still using LLM agents to do it. It's not like the LLM is somehow rewriting its own core transformer architecture from scratch. It's working within predefined parameters, however cleverly.
No, it's definitely working within parameters, but it's about pushing those parameters outward or defining them more optimally to get more out of the existing architecture. The focus here is on the meta-level intelligence, not necessarily radical architectural innovation every single time. It's a hard problem, Sam, and you have to start somewhere.
Okay, fine. I get the ambition. But let's shift gears to something a little more grounded. We're seeing a paper called Towards Surgical World Action Modeling. This one's about surgical robots, and it's trying to get them to predict both instrument movement and how the visual field changes simultaneously.
Right. This is critical for reliable surgical planning, where you need to anticipate not just where your instrument will go, but what the consequence of that movement will be on the tissue, on the patient, visually. Current models often separate these. Either they predict instrument trajectories, or they predict how the scene changes. They don't typically do both together.
Which seems insane, honestly. If you're going to cut something, you need to know where the knife is going and what the incision will look like. How could those ever be separate tasks in a real surgical setting? It's like having a map that only shows your car's trajectory, but not the terrain it's driving through.
Well, it's computationally intensive to model both. Separating them simplifies the problem. But as you point out, that simplification comes with risks. If your trajectory model says move left, but your scene model doesn't update consistently with that, or predicts a totally different visual outcome, you have a problem. This paper aims to bridge that gap by having a joint visual trajectory forecasting model.
And that joint model, is it actually better? Because adding complexity doesn't always mean better performance, especially in high-stakes environments like surgery. You want reliable, simple, robust, not necessarily fancy.
They show it's better at maintaining consistency between the predicted instrument motion and the visual evolution of the scene. And that consistency is what really matters for surgeon trust and safety. Imagine a robot that thinks it's moving an instrument away from a critical artery, but the visual prediction shows it actually getting closer. That's a catastrophic failure of consistency. So yes, the complexity here buys you reliability.
It's a pretty fundamental limitation they're addressing then. I mean, for a robot to truly assist in surgery, it needs to see the world like a surgeon does, understanding cause and effect visually as it operates. I'm actually a little surprised this hasn't been a standard approach already. It seems so obvious.
It's an active area of research for a reason. Real-time joint modeling in complex, deformable environments like the human body is incredibly difficult. And you can't just throw more data at it, because every patient is different. So they're pushing the boundaries on how these predictions are integrated.
Yeah, that's fair. The data variability in surgery is immense. Okay, so moving from surgical precision to something a bit more prosaic, perhaps. Let's talk about inducing task models from computer use traces. This paper is all about learning how everyday work is done by passively recording computer screens and actions.
This one really captures the making existing systems work better idea from our intro, Sam. The goal is to derive symbolic, auditable, and reusable models of how people perform tasks on computers just by watching them. Think about it. An agent needs to learn how tasks are actually performed, not just how they're theoretically supposed to be performed.
Right, but passively recorded screenshots and mouse or keyboard actions, that sounds like a privacy nightmare waiting to happen. And symbolic, auditable, and reusable models, are we talking about training agents or are we talking about monitoring employees to death? Because those are two very different outcomes.
The paper frames it explicitly for training computer use agents and for organizations to audit and reuse knowledge. The benefit is clear for agents. They get to see how humans actually navigate complex, multi-threaded workflows with interruptions and interleaved goals, which is far messier than any step-by-step instruction manual.
But even if the stated goal is agent training, the underlying tech for auditable models of how everyday work is done is a dual-use problem. Once you can record and model precisely how an employee spends their time on a computer, you open a huge Pandora's box of surveillance. And reusable knowledge could easily mean automating away these human jobs.
That's a valid concern, and it's something we always have to consider with these kinds of technologies. But from a purely technical standpoint, inducing clean, symbolic task models from messy, low-level event streams is a significant challenge. Real-world work isn't a single, linear workflow. People switch tasks, get interrupted, leave things half done.
So this method is supposed to untangle all that and model it so an agent can then replicate it. I'm picturing an AI agent learning to procrastinate based on my browsing history.
Hopefully not. The paper's focus is on dealing with that multi-threaded, interleaved goal problem. Existing methods often assume a given task or a single workflow, which isn't realistic. This approach tries to infer the underlying goals and subtasks from the chaotic stream of actions. It's about modeling the intent behind the actions.
And that's the hard part, isn't it? Inferring intent from just clicks and screenshots. What if the human is just messing around or confused? Is the agent going to learn that too? I mean, this feels like a powerful but incredibly sensitive area for development. We're talking about automating human work as it's actually performed, rather than as it's theoretically defined.
Precisely. The goal isn't to replicate human error, but to understand the context and typical deviations to make agents more robust and adaptable. It's a messy data set, but potentially a very rich one. Now, on to something that builds on our earlier discussion about meta-learning. We've got MidTool, which is focused on mid-training data synthesis for agentic tool use. This is about specifically tailoring the training data injected during the middle stages of an LLM's development to enhance its ability to use tools.
Okay, so mid-training is becoming a thing now. We've seen it improve math and science, software engineering. Now it's general tool use. So you're not just pre-training, not just fine-tuning at the end, but pushing specific data in the middle. What's the advantage of that?
The advantage is that this mid-training phase has shown to be incredibly effective for strengthening reasoning-intensive abilities. It's like a focused study period where the model is mature enough to absorb complex concepts, but still flexible enough to integrate them deeply into its core representations before it solidifies too much. And for tool use, where an agent has to understand API calls, parse responses, and integrate that into its reasoning, that focused intervention can be very powerful.
So, MidTool specifically is about creating an open corpus of synthesized supervision data that combines web, PDF, and code data with real-world tool APIs. That synthesized supervision part is what makes me pause. Is this just generating more realistic but still synthetic data to train on? How robust is that?
It's not just generating synthetic data for the sake of it, Sam. The key is synthesized supervision from real-world tool APIs. This means they're effectively using the actual outputs of real tools to create realistic training examples for how an agent should interact with those tools. So it's synthesizing the experience of tool use, grounded in actual functionality.
Right, so it's a sort of high-fidelity simulation of using the tool, but still a simulation. Does that translate well to actual deployment? Because tool APIs can be quirky, they can fail, they can return unexpected errors. Does the synthesized data capture that kind of real-world messiness, or is it always assuming the tool works perfectly?
That's a crucial point. The paper aims to build a corpus that reflects robust, agentic tool use. It's about giving the model a rich understanding of the mechanics and logic of tool interaction. If the agent understands the underlying principles of interacting with an API, how to call it, what to expect, how to parse, it's better equipped to handle anomalies, even if it hasn't seen every single failure mode. It's training for the paradigm, not just specific instances.
Yeah, but training for the paradigm with synthesized data often means you miss the dirty details. It's like teaching a pilot how to fly perfectly in a simulator, but they haven't experienced real turbulence or an engine failure. The real world has rough edges. I'm just wary of how much mileage you can get from synthetic data, even if it's API grounded, when you need robustness.
I think the argument here is that the sheer scale and specificity of this mid-training data, combined with its grounding in real API structures, gives a significant boost. It's about efficiently exposing the model to a massive variety of tool use scenarios that would be impossible to collect purely from human demonstration. It's an efficiency gain, for sure, but also a capability gain by sheer volume of targeted learning. And finally, let's talk about something that feels very different but ties back to our initial theme of subtle monitoring, a comparison between ceiling-mounted FMCW, IRUWW, and Wi-Fi radar for in-bedroom human activity monitoring and sleep interruption detection. This is about non-contact health monitoring.
This one caught my eye because it's exactly what you want for sensitive environments, like bedrooms, right? No cameras, no wearables, just passive radio frequency sensing. And they're comparing different technologies, FMCW, IRUWB, and Wi-Fi radar, all mounted on the ceiling, which is a really practical deployment strategy.
That's the key. Most studies compare these technologies, but often under different conditions, with different hardware, or in different environments. This paper is a controlled comparison, putting all three ceiling-mounted in the same bedroom scenario, trying to detect things like subtle movements, breathing, and even sleep interruptions.
And which one wins? Because from a practical standpoint, if you're going to roll this out in homes or care facilities, you need to know which tech is actually superior for accuracy and deployment cost. Wi-Fi sounds cheap and ubiquitous, but can it really compete with dedicated radar systems?
The paper actually highlights Wi-Fi sensing surprisingly well, especially for certain activities. For higher-level activity monitoring, like general movement, Wi-Fi can be quite effective. However, for very granular, subtle movements, like respiration or detecting specific sleep stages, the dedicated radar systems, particularly IRUWB, tend to show better performance.
So it's not a clear winner across the board. That's actually useful. It means you might choose your tech based on what you specifically want to monitor. If you just need to know if someone got out of bed, Wi-Fi might be sufficient. If you need to monitor their breathing rhythm for signs of distress, you'd go with something like UWB.
Exactly. And the ceiling-mounted aspect is brilliant because it minimizes obstructions and gives a consistent vantage point, which is crucial for reliability. It also means less clutter in a personal space. This feels like a really pragmatic paper, pushing towards actual deployable solutions for continuous, non-invasive health monitoring.
Yeah, I like this one. It feels less about pushing the theoretical envelope and more about making existing, valuable technologies truly practical and comparable for specific use cases. That's the kind of direct engineering that gets real-world traction, Alex. It's like the perfect antidote to some of the more abstract self-improvement stuff we started with.
Which, I think, brings us back to that initial observation, Sam. We're seeing a bifurcation. On one hand, incredibly subtle, meta-level improvements to AI's own learning processes.
On the other, incredibly practical, direct applications of existing sensing or modeling techniques to solve real-world problems.
Yeah, it's almost like we're simultaneously trying to build super brains and better invisible nurses. And sometimes those invisible nurses, in their directness and practicality, feel a lot more impactful in the short term, even if they're not quite as flashy.
I wonder if these two paths will eventually merge more significantly. Will the self-improving AIs become better at designing these pragmatic, specialized solutions? Or will the pragmatic solutions inform how we design the self-improvement mechanisms? It's an interesting tension to watch. That's it for the Robotics Brief this week.
Thanks for listening, everyone.
See you next episode. Take care.